How to calculate double integrals, part 1. Let's recall first the Fibini theorem. Globally, it says that if you have a function of two variables and you want to make a double integral to calculate the double integral, which is the volume, the algebraic volume between the plane, the domain, and the surface of the function. So if you would like to calculate such an integral, you have to go through two embedded integrals. So it will be the integral of the integral, which means that you have to integrate with respect to one variable first, let's say y, and then with respect to x, or the other way around. So you will integrate with respect to x first, and then with respect to y. But of course, you have to watch out for the boundaries. So you have boundaries in x and boundaries in y. That's why we'll take in the first example the case where the domain is a rectangle. So we have a rectangular domain. So the boundaries of x and y are just some constant values. This can be represented as follows. So we have a domain D in the plane x or y, which is in orange here. And then to this domain, or above this domain, we have a function that lives. So the double integral of f will be the volume between the domain and the function. And the boundaries in x are between a and b, and the boundaries in y are between c and d. Let's take an example to see how it works. So if we take a function f that is exponential minus x minus y, and we'd like to integrate it over a domain D, which is given by all the xy's in R2 such that x is between 0 and 1 and y is between 1 and 4. So let's say we decide to integrate first with respect to x and then with respect to y. Let us represent this domain in the xy plane. Of course, it will be the rectangle between x 0 and 1 and then y between 1 and 4. It's this orange rectangle that we can see here. Now, to integrate with respect to x first, this means that we will take a direction which is parallel to the x-axis, the one represented in green on the left figure or in green on the right one, and will integrate according to this green section. That's why you can see clearly that this green section is limited on the left by 0 and on the right by 1. So that's why we will have the boundaries for our integral in x that are 0 and 1. And this green section, if we move it like up and down, we can see that it will reach at the bottom the value 1 and on top the value 4. So the two small purple circles at the extremities of this section will be moving on two straight lines. The first one is x equals 0. The second one is x equals 1, which are the two boundaries we already put on the integral in x. And the minimum value it can get at 1 and the maximum value it can get at 4 will form the boundaries for my y integrals. So the y integral will be bounded by the value 1 and the value 4. Now the calculation will go as follows. So we integrate with respect to x first. We'll have minus exponential minus x minus y between 0 and 1. So we replace x by 1, then by 0. So replacing x by 1, we'll have exponential minus 1 minus y. Then by 0, we'll have exponential minus y. And this function will integrate it another time with respect to y. So we have exponential minus 1 minus y minus exponential minus y between 1 and 4, which will give us the last result. Now, if we would like to integrate the function by doing the integration with respect to y first and then to x. So it will be like taking, instead of the green section that was horizontal, we'll be taking a section that is vertical. So the integral will be written in the other way around. We'll have dy inside, dx outside, and then the boundaries of the inner integral will be 1 and 4. These are the boundaries of y, and then the boundaries of the outer integral with respect to x will be 0 and 1. Now, what will happen if the boundaries are not constants, so the domain is not rectangular? Then the boundaries will be dependent on each other. I mean, the boundary of y will be dependent on x or the other way around. That's why we'll integrate, if we decide to integrate first with respect to y, the boundaries of y will depend on x, and then the outer boundaries will be constants, or the other way around, if we decide to integrate with respect to x first, the inner boundaries will depend on y, and then the outer ones will be constants. Let's check an example about this. Let's take then the function x cosine y that would like to integrate on the domain given by all the xy's in R squared such that y is between x2 and 2x. So x2 is a parabola and 2x is a straight line. By the way, you always have to sketch the domain to decide which sections are you going to take, the horizontal sections or the vertical sections. In other words, what would you like to integrate first, y or x? It depends on the complexity of the domain. So anyway, let's sketch the domain here. We'll sketch first the parabola, so that's y equals x2, and then the straight line, y equals to x, and here is our domain in orange. Now, let's say we would like to integrate with respect to y first. This means that we'll take a section, and this section will be vertical, that will cut the domain, to be able to integrate with respect to y first. So what do we do in this case? The domain is not rectangular. we draw the section vertically, we take it, and then we move it right and left while keeping it vertical. So the extremities, the purple extremities of the section, will be moving on which two curves? They will be moving on the curve y equals x2 in the bottom and y equals 2x on top. That's why y equals x2 and y equals 2x will be the boundaries of my inner integral in y. And watch out, when the integral is in y, then the boundaries will be written as y equals something in terms of x. So in this case, it will be y equals 2x at the top and y equals x2 at the bottom. Then, if I take this section and I move it to the left, to the last point at the left, it will get which point in values of x? It will get to 0. And to the right, it will get to the value 2. So 0 and 2, the minimum point I can get to the left and the minimum point and the maximum point I can get to the right will be the boundaries of my integral in x. So this is how I can define, or I can use the Fubini theorem to write my double integral as two embedded integrals. I will have always the inner integral with boundaries that eventually, if the boundaries are variable, are not constants, they eventually depend on the other variable x, and the outer boundaries are always constant. So now we should proceed in the calculation. Now it's a standard calculation. I have to integrate x cosine y with respect to y, which will be x sine y. Then I will replace by the boundaries 2x and x2. And then I will integrate once more, like each one of them alone, in terms of x. The first one is x sine 2x, so I need to integrate it using integration by parts. And the second one is x sine x2, which is like u prime. It needs just a factor of 2 times sine of u. So the integration by parts for the first one, by taking u as x and u prime as 1 and v prime as sine 2x and v as minus half cosine 2x, will lead me to this result. And I still have one integration to do for cosine 2x, and this will lead me to the final result, which is minus cosine 4 over 2 plus 1 over 4 sine 4 minus half. Now, what if I would like to integrate with respect to x first and not y first? So I go back to the domain, and I will try to rewrite my integral in terms of x first. That's why I need now to take a horizontal section with its extremities at the right and at the left, and I will take this section and I will try to move it up and down. So the extremities of this section are moving on which two curves? On the left, I'm moving on y equals to x, and on the right, I'm moving on on y equals x2. That's why these two curves will be the boundaries of my inner integral. But as we said before, these boundaries should be written, since I'm integrating with respect to dx first, then these boundaries will be written as x in terms of y and not y in terms of x. So the left boundary is y equals 2x, then the bottom boundary here will be x equals y over 2. The upper boundary is on the curve y equals x2, so if I want to write it in terms of x, in terms of y, it will be x equals square root of y. So these will be my inner boundaries. Of course, the x equal, I will remove it, I will not write it. So I write y over 2 and square root of y. And then this blue section, if I take it to the top, it will reach the value 4, and to the bottom, it will reach the value 0. So 0 and 4 will be the boundaries of my outer integral. So again, when I'm integrating with respect to dy first, my boundaries will be y equals in terms of x for the inner integral, and when I'm integrating with respect to dx first, I will be having boundaries written as x in terms of y and not y in terms of x for the inner integral. So dy dx means vertical sections, means y equals in terms of x in the boundaries for the inner integral, and dx dy means horizontal sections, then x equals something in terms of y for the boundaries of the inner integral.